Hi, my project is called Gate-Level Logic Simulation with GPGPUs. I work with my mentor DPC and Professor Batako. So, what is simulation? And for a hardware designer, when he designed the network using HDL, we need to synthesize it and verify it. So the main part is that we need to check the equivalence of the function and our original design. That is mainly simulation. But the problem with this part is that the netlist simulation is extremely slow. That is just the problem we want to solve. And the solution we provide is we use the architecture called CUDA, which is invented by the company NVIDIA. And so for this architecture, we have a main memory called global memory, and we have many stream processors, and several stream processors is organized into multiprocessors. And also, there is a shared memory in the multiprocessors for each stream for access of each stream processors. And some features are that all threads could execute the same program, and the stream processor can access different memory locations based on the thread ID. And there is some different feature for the different pieces of memory. For the same memory, it's very fast. It could be accessed in one cycle, but there is only limited memory there. For the global memory, although there is a large chunk of global memory, but the access time is very slow. Okay, so what is our event-driven simulation? So it's a levelized netlist, and the input change value creates new events, and this event propagates if the output of the gate changed. So this requires a central control for the scheduling gates, and the scheduler needs to maintain the event queue, and also the scheduler should work at a fine granularity. Otherwise, it will cause a great overhead for the GPU. Then, which means the performance of our simulation will be reduced. So our project needs to find a fine granularity for this scheduling. And so from the GPU perspective, individual threads will simulate individual gates, and the small fraction gates are simultaneously active, and the frequent synchronization across all threads is needed. And how do we get a better granularity? We group each thread block simulates into a macro gates, and that is an independent chunk of logic. And the internal net values are stored in faster shared memory for performance. That's also the benefit of macro gate. And how do we carve the macro gates? First, we levelize all the nets based on the at least as possible scheme, and then we partition the levels into layers. And third, we get the coins based on the nets on the layer boundary. And last, we will merge the coins together to get our macro gates. So this is the picture for our netlist. For our netlist, we have primary outputs and register inputs. We also have primary inputs and register outputs. First, we levelize them based on as least as possible, and then we based on a specific get value, we partition the levels into layers. And then as you can see in the middle, there is a coins, and then we merge the coins into each coin has only one output, and then we merge the coins into the macro gates. And for the each macro gate has multiple input and output, not like a gate, but they are very similar. The events are monitored. As the macro gate boundary, and the nets on the boundary are called the monitor nets. So we will check the monitor nets to see which macro gates on that layer should be executed at each cycle. And inside the macro gates, we also levelize the gates. And so for each level of gates, we put a synchronization barrier there to ensure that all the data is ready for the next layer. So how do we build the macro gates? There is some problem there, because if the nets in the macro gates is not close enough, or the coins in each macro gate in the macro are not overlap, then we need more. Then we cannot guarantee that we have a great parallelism. So first, in each layer, we pick the coin with the most nets, and then we will check the nets with the maximum overlap with our current coin, and then we merge them. So we repeat this process until we have enough nets in the current macro gates. Then we return the initial step, pick the coins the coins in the remaining group with the maximum nets, and then we will check other coins. So how do we balance the macro gates? We want all the threads working at all threads, and we need to rebalance gate schedule within a macro gate to increase utilization. And this is a trade-off latency for utilization. So after our balance, we make sure that we have fewer idle threads in each macro gate. So this is the total net, the general net structure before we send the netlist into the GPU. And then this is the compiling part. After another feature of the current project is that we separate the process of compiling and running. So there is several benefits. First, we can reuse the compiled netlist to test different kernel designs. And second, we can get the actual kernel running time. And last, since some netlist is large and the compiling time is relatively long, and this separation could improve our research efficiency. So next is our kernel part. In the GPU, the running part is called the kernel. There are three parts in the kernel. First, we need to simulate the netlist, and second, we need to schedule the triggered kernel, and third, we need to schedule the input and read output in each cycle. So my project currently at this stage, and unfortunately we haven't got our main result, and we don't know how fast how faster we can get the simulation. So thanks for listening.